So now we're revisiting Maxwell's equations, and this time we're going to touch a little bit on the physical interpretation.
Yeah, Maxwell is a pretty confusing business.
Yeah, so we've seen some of them before, but hopefully we can erase some of the confusions without erasing the equations.
That sounds great to me.
We have 4 equations, and the first 2 are with the divergence. And so we recognize these as the differential form, basically, of Gauss's law. You can see that here we have all charges that create sprouting field lines from the charge. And we can count the number of field lines. The more charges, the more field lines. The second equation is del dot B is equal to 0. Some asymmetry here.
Yeah, I wonder what that means.
Why is this 0? Well, there are no single magnetic charges. Magnetic charges, quote, always occur in pairs. Like you have a North Pole with a South Pole. You never have a North Pole all by itself. So the divergence of B is equal to 0. Does that have any other result? The fact that there are no single magnetic charges. Whereas you can have single electric charges.
Yeah.
So the field lines are going to be different. What are the differences between the E field lines and the B field lines?
So the B field lines always have to meet back at some point from the North Pole to the South Pole, it comes back. But for a single point charge, you can have it emitting E field.
Everywhere.
Yeah.
Like,
and they don't need to come back.
So these guys are closed lines. And these guys can go out, radially out of a single charge. So these are radial. And these are closed loops. So those are the first 2 equations. A lot of times when we're looking and studying in this course, this side will be equal to 0. And these will be just constraints on the fact that there's no outward flowing of flux of stuff. Now we have 2 equations left. Curl of E is minus mu dH dt. So this is the curl operation. Different from this, which is like a dot product. This is a cross product. Same here. Faraday's and Ampere's curl equations with the curl of H related to all the current densities, which we'll go through in a minute. The curl of E, Faraday's law related to the time rate of change of H.
So what does the curl mean?
What does the curl mean? Well, just stand there. I'll try to figure it out. No, I'll try the other way.
Wait, are you orbiting me?
Yeah, the curl has to do with rotation. And we're going to look at that in great detail later on. What's the source of that rotation are these current densities. So for the source, a generator, we're going to often in this class assume that it's 0. This J is equal to sigma E is actually Ohm's law. And if sigma, the conductivity is very low, that's like an insulator, so this is going to go to 0. So this is 0 for an insulator. And this one is the displacement current. It's a source of circulating magnetic lines due to a time-changing E field. And that's really amazing because there's no sort of physical basis for this. This was all intuition. This was Maxwell's genius. So remember that when you encounter the equation again. He's the guy who filled it in. And as a result of this, combined with this, creating curls in both E and H, we're going to get waves. Without Maxwell's genius, no waves. He predicted them 30 years before they were discovered in a lab.